Okay, so we now have an expression for the fields radiated by a point charge. And so what we're going to do in this video is actually, use that expression and try to find some properties of it, try to calculate some other secondary parameters of interest. And to do that, again, I'm going to be using the non-relativistic expression. So that's the electric field which we just derived. And that's the non-relativistic expression, and that's the magnetic field. Again, to get here, we took the relative, the correct expression and set, beta almost equal to 1 and beta almost equal to 0 and kappa almost equal to 1. Again, it goes without reminding that all of this has to be calculated at the retarded times. And so, it's kind of annoying to carry this all the way. So I'm going to be dropping it sometimes, but just be aware that whenever we calculate fields from particle trajectories, it's always at the retarded time. Okay, so just for notational simplicity, I might drop this retarded everywhere. Let's just look at some of the properties of it. So if you look at the magnitude of the electric field, that is just q sine theta beta dot by CR. So what is theta here? Well, theta is actually what comes out of this expression. So theta just happens to be the angle between B dot and the observer. So the observer being the point where you're calculating the electric field. And they're just easy to see. So N is basically the direction of transmission. So N is really the position vector from the particle to the observer. So N cross beta, in this case, beta dot. So N cross beta dot in this case is going to be pointed into the plane of the paper, and then N cross of that is basically going to be, in the plane of the paper in this direction, which I am showing E. And of course, N cross B, the magnitude of this is sine theta, right? It's just the cross product. So that's where the sine theta comes from. So that's the magnitude, and the direction of it is in the plane of the paper. And B is N cross E, right? So E, B, and N have to form a right-handed set. So B is basically going to be pointed out of the plane of paper. So E cross B is going to point towards the direction of radiation. So easy way to identify the vector E, the orientation of the vector, is to recognize that E lies in the same plane as beta dot and N hat. So it lies in the same plane as the acceleration vector and the line of sight vector. And it's always parallel to the acceleration vector. So that's an easy shorthand to figure out what is the direction of E. And of course, you can get B from B being N cross E. So it's a convenient way to write E is this. Okay, so once we have the electric and magnetic fields, we're talking about the radiation fields here, not the Coulomb field. I've only taken the radiation part. We can ask ourselves, what is the Poynting flux? So we can calculate the Poynting vector S. So that is C by 4 pi times E cross B. And the Poynting vector is pointed in the direction in which the energy is being transported. And it's basically a measure of the energy flux, right? So it's ergs per second per square centimeter. So it just tells you per square centimeter aperture how much energy is being transported in some given direction. So yeah, you can plug in for B here. B is N cross E. And so it's just immediately obvious that the Poynting flux is C by 4 pi times E square, and N is just the direction in which the vector pointed. So that's just N hat. Again, E square is easy to calculate. So that's basically the amount of Poynting flux which a charge radiates. Again, all of these only depend on the acceleration of the charge. They don't really depend on the velocity of the charge. They only depend on the acceleration. And of course, the Poynting flux goes as R square. So, that must be familiar to you from first chapter where we actually did flux density calculations. And then you can remember how you took the luminosity and then you said, I'm going to divide that by 4 pi R square and get the flux density. Again, that R square always appears, right? And it's there in the Poynting flux too. So that all hangs together and makes sense. The general idea that flux density goes down as 1 over R square. We can calculate what is the instantaneous power. So this is just the total power radiated by the charge. And to do that, you just have to take the Poynting flux and integrate it over some surface area, right? And then you get the total power, because the Poynting flux is just the energy per unit time per unit surface area. And then you just integrate it over, some closed surface. And that's what I've written here, some closed integral. And, in this geometry, it's simple to just take this as a shell and integrate this over a shell. There are a few ways you can do it. But this is one way I'm going to do it. So this is just the Poynting. This is just the Poynting vector from previous page. I've just written that down, and then it's in the direction of n hat. So I'm just going to dot that with an area element, and the area element again, is pointed along n hat. So n hat dot n hat is just going to give you 1, and then this is the differential area element. Is in a shell, it's just going to be r square times d omega is the differential area element. So r square and r square cancels. That makes sense because the total power radiated should not depend on how far you are from the object. That's just the total power radiated by the object. And then, yeah, you're only left with an integral of sine square theta on a sphere, right? So sine square theta d omega. You're going to encounter this integral a lot. I think it evaluates to 8 pi by 3. So it's nice to remember that sine square theta integrated on a sphere is 8 pi by 3, because you're going to see it again and again. But the basic steps are easy. I mean, the phi integral just gives you 2 pi. And then the theta integral is d theta sine theta. That's the differential element times sine square theta, our integrand. So you're basically integrating sine cube theta. You can integrate sine cube theta by basically writing sine square theta as 1 minus cos square theta, and d theta sine theta as d cos theta, right? And then it just becomes a polynomial integration. It just becomes an integration of 1 minus x square. And that comes to 4 by 3. So yeah, 4 by 3 times 2 pi is 8 pi by 3. You put all of that together, you get the total power radiated. So that's the amount of energy per unit time. And again, important things to note is it depends on the square of the charge, and it depends on acceleration square. Again, no dependence on velocity. All the radiated fields come from acceleration. So that's a very simple and handy formula to calculate the total power radiated by any accelerated charge. And we're going to be using all of these in the rest of the course, because we are just going to do different emission mechanisms. And the way we do different emission mechanisms is we're going to go to a single electron, which is doing the emission, and we're going to say how is the electron being accelerated. And we're going to solve the dynamics of the acceleration depending on what the mechanism of emission is. And then we're just going to plug in these formulas to basically get the power, the spectrum, which I'll come to soon, and all of this. So this video is just to set up all of these things, which we're going to be using when we actually go to different emission mechanisms. So to give you an example of how all of this will be applied, so if we do Bremsstrahlung, which is just the emission of a plasma, where the emission happens because electrons and protons kind of collide, quote unquote collide. And that is nothing but the electron being accelerated in the Coulomb potential of the proton. And so once you have the expression for the acceleration by solving the dynamics of an electron moving in the Coulomb potential of a proton, yeah, then it's just straightforward. We'll just use expressions from this week to work out the different properties of emission. Okay, so the next thing I want to talk about is an approximation which we'll be using a lot. It's called the dipole approximation. And the basic idea is this. Let's say that we have a system of charges. It can be many charges. It can be a single charge. It doesn't matter. And we say that all these charges are moving, but they're moving within some volume, which has a linear size of L. Okay, so that's what's happening. So if you have a single charge going in a circle, then L is just the diameter of the circle. You can have a charge cloud. So it's just a cloud of charges which are all moving and radiating. And they're all contained within a volume of size of linear extent L. And let's say U is the sort of the characteristic speed of these charges. So U is the speed at which the charges are moving. Of course, it's not that every charge has the speed U, but U is just a scale. Is it a tenth of the speed of light, a hundredth of the speed of light? It's roughly an order of magnitude kind of a quantity. Now, the time scale of variation. So this is the time scale over which the emission is varying. is just given by the time scale over which the particles are moving, right? Because when the formula we derived showed that the electric field, the temporal variation of the electric field just depends on the temporal variation of the acceleration. So it just depends on the temporal variation of the motion of particles. So that time scale is roughly going to be L by U, because L is the, the scale of the distance the particles travel, and U is the speed at which they're traveling at. Now, the frequency of emission, so kind of the spectral content of emission, is going to be of the order 1 over tau, and that is going to be U by L. Now, let's say that the motion of all these particles are non-relativistic, right? So that means that U is far, far less than C. So you immediately get that tau has to be far, far greater than L by C, because tau is equal to L by U. Tau is equal to L by U, and U is far, far less than C. So tau far, far greater than L by C, which means C by nu. So nu is the frequency, far, far greater than L, or I mean, this is just the inverse of the wavelength. So wavelength far, far greater than L. So what is this saying? This is basically saying that, sorry, this is not the inverse of wavelength, that's the wavelength itself. So this is basically saying that as long as, the length scale over which the charges are moving are small compared to a wavelength, this condition is going to hold. Okay, so this condition which I'm specifying for particles to be non-relativistic basically transforms into, it's equivalent to saying that, the size over which the particles are moving, the length scale over which they're moving, are far, far less than the wavelength over which they're going to emit. Now, an interesting consequence of that is because light or information is moving at the speed of light, but these particles are moving extremely slowly. One consequence of this is that the internal retardation within the volume L, you can ignore that, and you can just use a common retardation for all the particles. So what do I mean by that? What I mean is, let's say you have two different particles here, they're both doing their own thing. That means that for an observer far, far away, situated somewhere here, the observer is going to see different amounts of retardation from the two charges. Now, as long as this condition is satisfied, that difference in the amount of retardation is so small that you can basically ignore that small difference and just use one common retardation for the entire cloud of particles. Okay, so that works even if you have a single particle. Let's say you have a single particle doing orbits in this volume. What that means, again, this condition, what it says is that for different parts of the orbit, you can just use one common retardation, and it wouldn't make much of a difference. So you can think of this in terms of time retardation. You can also think of it in terms of phase of the electromagnetic wave which the particles are emitting. Again, when you think of phase, this makes more sense. When lambda is far, far greater than L, lambda, remember, is the length over which the phase varies by about, the phase goes through one whole cycle. So it varies by about 2 pi radian, right? So that's the definition of lambda. And so what this is saying is that if all these particles are within a small volume, then even though they're independently moving, all of their emission is going to, quote unquote, add in phase. You can use a common phase to represent the phase of the outgoing radiation of all of these particles. So you can kind of forget about the internal minute differences in phase of the emission, which you're going to observe from a large distance. Of course, that doesn't hold unless if you're in a very close distance, and if you're inside the cloud. All of this applies when you're at a large distance. Okay, so just to put this in terms of equation, so here we have the equation for the radiated field, and now I've just made it as a superposition of the radiation of all the particles in that volume. And I is the index for the particles, so it's n cross n cross. Actually, this should be ui dot. I'm sorry, I forgot a dot here. So u is just the velocity, so ui dot is the acceleration divided by the distances. Now, when we use the dipole approximation, first of all, we can just replace the individual distances by a common distance r0, let's say to the center of the volume. The other thing we can do also is basically define something called dipole moment. Okay, so this is D is the dipole moment, and D is basically defined as a kind of a charge weighted sum of positions of the particle. So Ri is the position vector of the particle, Qi is the charge, and D is just, summation of Qi times Ri. So you can just think of it, the dipole moment, as kind of a charge weighted sum, vector sum of the positions of all the particles inside that volume. And of course, I've gotten rid of the, the retardation here, because I'm just going to, in the end, apply a single retardation, right? So we're going to have a common retardation for all of the particles in the dipole approximation. And so this expression, again, so you need ui dot. So ui itself is r dot. So what you have here is the acceleration, which is the second derivative of distance, right? So you basically have the second derivative of the dipole moment. And so it's just convenient to, you'll see when you work out problems that it's just convenient to have the dipole moment. By the way, it doesn't matter what origin you choose here, because you're going to take the second derivative. So any constant offset vector is going to just get differentiated to 0. And so that's the radiated electric field in this dipole approximation, which we just spoke about. Yeah, so again, we can basically work out the Poynting flux in this case. So this is the Poynting flux, which we calculated last week. Again, it's, energy per unit time per unit surface area, and it's pointed orthogonal to the, it's actually pointed along the line of sight to the observer. Now, again, we can go through exactly the same, again, it's exactly the same calculation which we did for a single charge. I'm just doing it and expressing it in terms of the dipole moment. So energy per unit time per unit area. Again, that sine square theta factor is just the n cross d double dot here, where d double dot, the vector, is pointed in the direction of the acceleration. But now in this case, it's basically the average acceleration, right? Because we are talking about an average quantity here, which is the dipole moment. Again, yeah, I mean, the procedure is the same. You can write the area dA as d omega times r naught square. R naught square cancels from both sides. And then you get amount of energy per unit time per unit solid angle. Again, you integrate that over solid angles. Integral of sine square theta is 8 pi by 3, like I just mentioned. And so you get the power radiated in the dipole approximation. This is the total power radiated by a collection of charges in the dipole approximation. Okay, so the last thing I want to talk about for this video is the spectrum of the emission in the dipole approximation. So if you remember, so far we've only been talking about the electric and the magnetic fields as a function of time. Now, suppose you have a case where there is some kind of a periodic motion of a charge. So let's say a charge is oscillating or it's going in a circle, some kind of a periodic motion. Then it becomes easier to express all of your time quantities as a spectrum, because when there is simple harmonic oscillation, there's just a single frequency. The other way, there are other cases where you want to look at things in kind of a frequency domain, even if you have a case where you don't have simple harmonic motion, for any number of reasons, right? I mean, it could just be for a practical reason, because you're measuring the spectrum of emission and trying to deduce something physical from that spectrum. So you want to have kind of a formalism to convert all of these things, the formula for the radiated energy of a particle, the electric fields, and all of that into spectral representation. So again, we start with the time domain representation, which we just solved for. So electric field is second derivative of the dipole moment. Of course, this sine theta is just the n cross d double dot, just gives, that's where the sine theta is coming from. And again, I've dropped the vector nature here. I've just taken the scalar value. And so what I want eventually is E of omega, right? I want the spectrum of the electric field. And so the question is, how do you get the spectrum of the electric field? Well, it's obvious. You can just take Fourier transforms on both sides. And then, you can work out what the spectrum is. But of course, if you take the Fourier transform of D double dot, we want to express that in terms of the Fourier transform of D itself. And that's fairly simple. So D of T is the inverse transform of D hat. So this is the spectral representation of the dipole moment. and that is just the Fourier relationship. So if I differentiate with respect to time, here I get d dot, and on the right I have d by dt, which I can push inside the integral. And again, d hat of omega doesn't depend on time. And so I only have to differentiate this with respect to time. I get back the same exponent times minus I omega, right? Using the chain rule. Again, I can do it twice. I get another I omega, so it's basically minus of omega square times, d hat of omega into the I omega theta. So the Fourier transform of twice differentiated quantity is just omega square times the Fourier representation of the undifferentiated quantity. And you might probably know this result already from before. So yeah, so we can basically write E of omega now. So instead of just having d hat of omega, we now have omega square, because we were taking the Fourier transform of d double dot. And so yeah, that's where this omega square comes from. And so this is the Fourier transform, or the spectral representation of the electric field. Again, from last week, that the total energy radiated, by again going through the Poynting theorem, the Poynting vector, the energy radiated per unit area, not per unit time now. Right now it's per unit frequency, is just c times E hat of omega square. So you can just substitute that here. So we have E in terms of the Fourier transform of the dipole moment. So you can just substitute that here, square it, and there you have it. You have d by d omega dA. We play the same trick again. You can write dA as d omega, the solid angle, times r naught square. So r naught square basically goes away from both sides, and you get the final expression. So the spectrum of the emitted radiation, so this is ergs per hertz in this case. So it's the amount of energy per unit frequency bin, is given by this expression. So 4th power of frequency c cube, and like you see, you have the square of the dipole moment. Sorry, the Fourier transform of the dipole moment. Now the interesting thing here is the spectral content you have is just equal to the spectral content of the dipole moment. So let's suppose that the dipole moment had a single frequency in it. So for a perfectly oscillating charge, you just have a d hat of omega is just a delta function, right? So will the emitted spectrum be. So what this is telling you is that in the dipole approximation, whatever spectral content is there in the movement of charges, the same spectral content is there in the radiation they're emitting. And just to remember, this only applies to the dipole approximation. Okay, if we don't make the dipole approximation, all of this falls apart. And you'll actually see when we do synchrotron emission that when the charges are relativistic, so we can't use the dipole approximation, you'll actually see that even though the charge is doing a simple periodic motion in a circle, its emission is not at a single frequency, the frequency of gyration. It actually has a lot of different spectral components. And so this doesn't hold. But at least when the charges are non-relativistic, in the dipole approximation, this holds. So if you have emission which is a harmonic oscillation, let's say, so it's just oscillating at a single frequency, the electric field is also going to oscillate at exactly the same frequency. So the power content, so if you just measure the electric field and say what is the power per unit frequency, you get the delta function there too. You have power only at that particular frequency. Yeah, so that's dipole approximation, which is going to be widely used. And these are just different formalisms which we are going to use when we actually do practical problems, where let's say D is specified, right? So I specify D in a given problem, and then we're going to calculate what the properties of the radiation are.